In the year 1844, a German mathematician, Hermann Grassmann, published his theory of extension. His discovery led to a branch of mathematics we know as linear algebra, which is the study of linear vectors using matrices. In standard math, the definition of a vector is a quantity having a direction as well as a magnitude. However, in linear algebra, a vector is a list of numbers that could be transformed through operations. We can also visualize vectors as a line in space with its tail pointing at the origin. A 2D vector could be represented by a 2x1 matrix, one value for the x-coordinate and one for the y. One of the operations we can do with vectors is vector addition. In order to add two vectors, we simply add the corresponding values to get a new vector. You can reach the same answer by putting the tail of one vector into the other. Another useful operation we could do is scalar multiplication. When you multiply a scalar by a vector, the vector stretches or compresses. For example, if we multiply this vector by 2, the new vector will be twice as big. If we multiply it by 3, it would be 3 times as big. Similarly, if we multiply our vector with half, the vector will compress to half of its original size. Both vector addition and scalar multiplication is very useful in many applications, but what really makes linear algebra interesting is vector multiplication. To multiply matrices, you do this thing where you multiply the rows of the first matrix with the column of the second one, and then you add them up. You do that for all of its values. Because of this, the number of rows in the second matrix has to match the number of columns in the first one. This is why matrix multiplication is non-commutative. Multiplying matrices allows us to transform a vector in a way that was not possible with matrix addition or scalar multiplication. For example, if we want to rotate this vector 30 degrees, we can multiply with this vector. If we wanted our vector in 3D space, all we need to do is add a third value for the z-axis. Without vectors, computing 3D graphics would have been extremely complicated and would have required tons of computing power. This is why linear algebra is so important in computer science and robotics, because 3D space could be easily mapped and transformed using vectors. The graphics you see in your computer is a result of your computer multiplying many matrices every second. Vectors are most useful in physics, because physicists often need to work with more than 3 dimensions. Even though matrices seem to be an abstract form of math, without it, our phones and computers won't work. Industrial machines that build our cars, pack our food, and process our data won't function, and many discoveries in modern physics won't exist. And that is because we live in a universe with multiple dimensions, and linear algebra allows us to process information in a multi-dimensional space.